BBC Two steps gingerly into the dangerous world of volcanoes now, in Seeing Through Science.
Molten lava from the inside of the Earth. From this, the first mountains were created. For years, humans have watched with wonder, but now science is enabling a few small steps more. The possibility of altering events. We're going to find out just how much we now know about the way volcanoes work, and about how these great destructive streams of lava might be diverted. First stop, a tropical beach created just 2 months ago by a volcanic eruption.
This beach is one of the newest places on Earth. The thing started about 15,000 million years ago, with the Big Bang. If this line represents time from the Big Bang, or this coconut palm, then every pace that I tread is about 150 million years. So I think we're going to need to speed things up a bit. Here the Earth would have been formed about 5,000 million years ago. The first signs of life, and then the animals came to land. First amphibians, then the dinosaurs. On this scale, each grain of sand represents 100,000 years. Here the dinosaurs became extinct. Humans arrived, and here we are now, today.
This means that volcanoes have been active and changing the landscape for 4,600 million years.
So the mountains on the Earth have been forming over this huge timescale. Can we really expect to change these processes?
To answer that question, we need to travel to the middle of the Pacific Ocean, to the tropical island of Hawaii. Kilauea is one of the most active volcanoes in living memory. Since at least 700 AD, when the first settlers came from Polynesia, there have been eruptions here. In 1912, right at the top of the volcano crater, they built an observatory to monitor what was going on. Researchers here probably know more about the science of volcanoes, volcanology, than anyone else. Dave Clegg is in charge of the US Geological Survey Hawaiian Volcano Observatory.
Morning, Kelly.
Hi.
I asked him what the role of the HVO was.
The first order role is really public safety and protection of people's lives and property. And the way we do that is by monitoring the volcano and the earthquake activity on the volcano. And then we interpret that based on the way the volcano has behaved in the past. When we saw something happen, then something else would happen. The second is what allows us to do the first, which is to really understand the volcanic systems. And to do that, we're really doing science and understanding what's going on within the system by looking at all types of data that we record in the field. You really normally start with an idea of what you think is going on, and then you go out and you try and collect the data that will tell you whether you were right or not. And if you weren't right, then you start over again with a new idea. And if you were right, you pat yourself on the back and move on. What you're looking for is changes in the system. I think it's really important to keep track of everything that's going on, because if you go out to test a single idea and you're looking for a single thing, either you will see it or you won't see it. Whereas if you keep your eyes open, you'll see new things that will help you define what the next things are that you want to do.
Exciting stuff. But why are there active volcanoes in Hawaii? Deep inside the Earth's crust lies the mantle. The rock material here, called magma, is under such great pressures and temperatures that it behaves like a liquid. Like liquids, when it's hot, it moves in a motion called convection. These convection currents create hot spots, which can enable the magma to rise to the surface and erupt. But what happens to the lava then?
When it comes out of the vent, there is a range of eruption styles that it can take. And that really depends how much gas is in the lava and how the gas comes out of the lava. So the eruption itself can be quite spectacular, throwing lava thousands of feet into the air, or very passive, where literally the lava flows out very quietly onto the ground. You don't lose any heat in that process, and so the lava tends to remain quite fluid. It will then form a channel, and eventually the channel will form a roof, and as the flow continues, it will become completely underground, as the current eruption is.
These underground lava tubes can sometimes be seen through skylights, gaps where the roof of the tube has collapsed. Down there, the lava is flowing at 0.5 meter per second, with a temperature of 1,100 degrees Celsius. So far, this lava has taken 6 hours to get here from the vent 11 kilometers away. It then enters the sea, causing clouds of steam laden with hydrochloric acid mist. That flow speed depends on how steep the slope is and on the viscosity or thickness of the lava. Viscosity is set by the temperature and how much gas the lava contains. Hawaiian lavas are very hot and contain lots of gas, so they are thin, less viscous. But in other parts of the world, there are lavas which are more viscous. The thickness of the lavas and the speed at which they flow then decides the types of lava's surface. The viscous lavas flow down quite slowly, covering everything in their path. The lava breaks into fragments and it tumbles like a slow-speed avalanche. It's called RR. In contrast, the other main type of lava surface is the pahoihoi flow. It's much more fluid, and with lots of gas, some escapes and ignites immediately. Cooled, the very thin, runny flow makes the smooth, ropey surfaces seen everywhere on Kilauea. Its gas bubbles can be clearly seen. Pahoihoi can advance very rapidly down slopes. But what happens when the lava hits an object? A tree, for example? Well, as the lava builds up, the surface of the tree cools it, making a solid coat. The flowing lava then runs away, leaving the tree cast, standing. By now, the inside of the tree is burnt away. It's fascinating and very beautiful. The petrified remains of an ancient forest. The volcanic rocks left behind by these lavas are called basalts. These rocks, and all others that come from molten magma material, are called igneous. Knowing the link between what you can see in a rock sample, its structure, and the way it was formed, helps scientists to be able to look at a rock and piece together what has happened in the past.
Oh yeah, I can feel that.
Yeah, probably broke out sometime yesterday, but it's not active anymore.
So for HVO geologists Tari Mattox and Beth Reinard, the rocks tell a more fascinating story. I joined them on a field trip, an investigative walk over the hot, flowing lava tubes to see where the Kilauea lava enters the sea.
Well, this really is the end of the road, and Tari and Beth are going to show me what lies ahead. What do you expect to see today, Tari?
Pretty much we're going to see a lot of old flows. I don't think there are any active flows out there today, but we're going to be walking across these old flows at the end of the road, and we have a time-lapse camera set up on the far side of the flows. And so our first goal will be to go out there and change the film in that. And then we're probably going to head back and take a look at these ocean entries here and see what's changed out there.
These clouds look a bit ominous. Do you think we ought to get going?
Yeah, we probably should.
Part of the excitement of this scientific work is the unexpected. This whole area could explode at any minute, or there could be breakouts of lava flow where you least expect them.
This looks like a new breakout right here.
It's pretty warm, isn't it?
Yeah, it feels warm.
Can I touch it?
Yeah. Try just carefully.
Oh, wow, it's very warm.
Oh, is
I
it?
can just about touch the end of that.
It's a little flow toe. This looks like what we call a pahoehoe flow. All of these flows out here are pahoehoe, and it looks like it was maybe active yesterday sometime. Just broke out and filled in this area.
So
And
we
then
could say
stopped.
this part of the Earth is 1 day old.
Yeah, you could say that.
Neat. Is this warm?
Yeah, it is a little. It keeps its heat for a little while, and but obviously the thinner areas in the flow are going to cool off fastest. But you can still feel the heat coming off of this flow.
We walk right across a lava flow, over a tube, and your camera's here waiting for us. What are you going to do?
Well, I need to change the film in this camera. It's a time-lapse camera, and it takes a picture every 3 minutes of the ocean entries. And so we come out once a week to change it.
What sort of other things do you do around here?
Well, we like to see what changes there are out here at the active bench. Part of the land every once in a while will slough off into the ocean, and so we're going to do some measurements of the dimensions of the area that's being built out. And just look for any changes, photograph any changes, that kind of stuff.
I'll let you get on with it.
Okay?
All right.
But I'll probably stop when I stop. Come up and join me.
Okay.
And we'll start again.
On other field trips, HVO scientists measure the temperature and speed of these lava flows. By measuring this, and then knowing the width and estimating the depth of flow, it's possible to calculate the volumes of lava that are being transported. Scientific work in these areas can often be uncomfortable and pretty dangerous. But most of the world's volcanoes are actually under the oceans. How do volcanologists investigate them?
In fact, that's just what this submarine is designed to do. Pisces 5 is about to go on a voyage of discovery.
These divers are controlling the liftoff of Pisces. It's a delicate operation. From now on, they're on their own. It's all part of a scientific investigation by the Undersea Research Lab at the University of Hawaii. "1,000 meters below the surface and 28 kilometers later, the submarine approaches Loihi, a volcano under the sea.
The volcano is growing at an extraordinary rate. It'll pop up to the surface within 50,000 years, we believe. And in geological terms, it's a very short time indeed. Submarine volcanoes are extraordinarily different from those that you see on land, primarily because the action of hot water interacting with the magma has allowed great big vast fields of bacteria to form.
So what's the difference between investigating volcanoes underwater rather than on dry land?
Well, on dry land you can go out and take a hammer and knock off a rock. Underwater you have to use manipulators that you operate from within the submarine.
And this rock is from Loihi, is it?
This rock is from Loihi, and the only sediment you see here are this orangey, clayish material we call nontronite, but it's actually been precipitated by bacteria.
It's likely that Loihi will eventually become an island. But why are the new volcanoes forming here? The answer lies in the way the Earth is composed of floating plates of rock that support the continents and oceans. On one edge, material for the continental plate is being created. This means that the plate is constantly moving. Meanwhile, over the Hawaiian hotspot, weaknesses allow a volcano to break through and a new island can form. But the movement means that the hot spot eventually rests under a new piece of plate, and so another volcano may form. This has created the Hawaiian island chain. But on the other side of the Earth, between Europe and Africa, things aren't so clear. The plate supporting Europe and the plate supporting Africa are moving towards each other. Scientists are not sure exactly what's happening, but some think that in the resulting squeeze, material may be being pushed downwards, resulting in the volcanoes in the Mediterranean, like Mount Etna.
Inch by inch, the lava flow creeps down the hillside into the outskirts of Zaffarana. Rivers of molten rock, sometimes 30 feet high, that have so far proved unstoppable. Every hour, the lava gets another 12 feet closer.
1 year later, in 1993, on the slopes beneath Mount Etna, Sicilian life carries on with a typical Italian normality. The people around here are devoted to the land. Crops grow well in the rich volcanic soil, and growing has always kept large numbers of people in work. This piazza is the central square of the Sicilian town of Zaffarana. Living here, Etna is ever present. But last year, the threat became very real. On the 14th of December 1991, an eruption began on the southeast side of the volcano. This time, the lava came not from the main crater, but from what's called a dike, a channel which runs out from the side of the main magma storage area. Viewed from space by the Landsat satellite on the 2nd of January, the lava could be seen advancing down the valley. By the 22nd of March, it was still on the move. The next stop will be the town of Zaffarana. To find out what happened next, I needed to go on an expedition to the summit. British volcanologist John Murray is an expert on the science of Mount Etna.
Well, my interest is in the deformation of the ground, the slowly changing shape of the ground before an eruption as magma makes its way to the surface.
How much does the ground actually move? I mean, could you see it moving?
Well, usually it moves very little. I mean, I suppose 2 or 3 centimetres a year is about average. But during eruptions, it can move a great deal more, and it moves up to 1.5 metres, more than that sometimes. The record is actually 4 metres displacement, which is an awful long way.
By measuring this movement as the magma pressure under the ground builds up, John has successfully predicted some of Etna's eruptions. It's a time-consuming job, so leaving me in the Land Rover to admire the view, John and his team went off to the summit.
The station should be over the back here. Somewhere here. Yeah, there's the nail.
These reference points have had their position calculated with great accuracy.
This station is Bozo and that one is Blue Bonnet.
All right.
They then serve as a marker to allow other positions to be mapped. Between the stations, changes in the ground surface of Mount Etna can be accurately calculated.
Okay.
The first task is to use a theodolite to measure the vertical angle. It's a dangerous job. John and the team limit their time here at the summit to minimise the risk of being caught by an explosion.
Okay, tell them we'll be ready in about 1 minute.
Okay, Blue Bonnet from Bozo. Can you get ready? We'll be ready in about a minute.
Roger, Bozo. 85 degrees, 50 minutes, 17 seconds.
John takes the reading and then swivels the instrument around 180 degrees and takes it again. This cancels out any inaccuracy in the equipment. They then put a reflector on the other station to enable the distance to be measured.
Blue Bonnet, we've finished reading onto you, so if you'd like to pack up and move down to IC11, we will stay put. Over.
Roger, Bozo. Over and out.
John's work is helping us understand Etna, but last year the need was for much more urgent action. That lava flow had to be diverted somehow. So what attempts have been made to do this in the past?
The very first attempt anywhere at stopping a lava flow or trying to divert a lava flow actually took place here on Mount Etna in 1669. The problem then was that a very big flow was coming towards the town of Catania. So the men of Catania came out with picks and shovels and broke open the side of the flow where it had frozen and let out the liquid red-hot molten lava inside so that it flowed out in a different direction. Unfortunately, that was towards the town of Paterno, so The next day, the men of Paterno turned up with picks and shovels too, but they were to hit the men of Catania with, and a sort of quite a fight developed.
That doesn't sound much fun. Are there any other ways to divert the flow?
You can also try and cool the lava to make it freeze more quickly. The 1983 lava here, which came down the south flank of Mount Etna, was threatening a lot of the tourist facilities. So what they did then was to use a similar method to what they did in 1669. They actually used dynamite to blow away the side of the flow to try and let out the red-hot lava inside.
Do you have a favourite method of diversion?
You try and divert the lava flow high up near its source, then it's going to take another 2 or 3 months before it will be threatening the town again.
But last year, dynamite wasn't enough.
Explosive charges were set off on top of the hardened shell of the lava in an attempt to form natural barriers to the flow underneath. Preparations have also been made for 2-ton blocks of concrete to be dropped onto the lava by helicopter. The whole operation has been hampered by land and property owners in villages around Zaffarana who've been trying to prevent the lava being redirected towards them.
Well, there was some success with the dropping the concrete blocks on the flow, but the main trouble is that most of them just sat on the surface of the lava and were carried down flow as if they were on a conveyor belt. The point is that the lava here is a very stiff kind of lava. It's not runny like in Hawaii. So you can, in fact, walk on it, and I have done that by accident once or twice, though I wouldn't advise it. It's very, very hot, obviously.
Despite this problem, the idea should work. Just as trees cause the lava to cool and form casts, so cold objects in the lava flow can create obstructions. These can then block and divert the flow to a new direction. But the viscosity of the lava is all important. The Etna lava was too viscous and carried the blocks away. In Hawaii, it probably would have worked. So what happened to Zaffarana?
They did have some success in they blocked some small flows, but at the same time, it was in May that rate of lava production did drop dramatically to about half of what it was. And although it continued to flow for a year after that, it never reached more than about 2 or 3 kilometers from where we're standing now. So it was no longer a threat to the town of Zaffarana.
Can I go and have a look where it did finish up?
Yes, let's go.
Wow. 6 kilometres and loads of dust later, it's actually ended. What made the lava stop flowing just here?
Well, it has travelled a great distance, 6 kilometres, and it is cooling the whole while. And of course, there eventually comes a point when it all reaches its solidification point, and it's stopped just in front of this house here.
So it's dangerous, as well as eruptions, there are constant earthquakes. But the economic advantages of good crop-producing soil, cheap building materials and tourism mean that people want to stay. Mount Etna's part of their lives. These steps are made of lava. They even used lava when they made the church behind me. So given that they want to stay, how can science help to let them know the dangers and when and where an eruption is likely to occur?
It's really like the weather. It's a very, very complex system, and you can get it right perhaps most of the time, but it's so complex that even if you had all the instrumentation you wanted, I think there's going to be an element which is going to be difficult to predict, a kind of random element.
It will allow us to be much more active in anticipating what's going to happen and therefore being prepared for it. And this can be things that are now being attempted, such as lava diversion, or they may be things that we haven't even thought of yet, of actually being able to change the area where the lava is erupting in some way so that the flows go in a totally different direction.